The third podcast on chemical equilibrium has to deal with applications of the equilibrium constant. Now, what we're going to see here is calculating Keq with initial amounts. So in our chemical equilibrium problems, we will always start with zero products for simplicity. This way we know the products will increase in concentration and the reactants will decrease in concentration. Now, a more advanced class will not assume the same situation, and you'll have to calculate Q and compare it to K. So in this class, we're just going to assume that we have no products at the beginning and that we know that those products are going to be formed and reactants are going to decrease in concentration once we reach equilibrium. All right, so let's get started. When given initial amounts of reactants and products, we need to determine the amounts of reactants and products at equilibrium. We will either solve for or use Keq and an ICE table to accomplish this. Now you're probably thinking, what does ICE stand for and how do we use it? Well, an ICE table looks something like this given the equation up above. The ICE stands for initial, change, and equilibrium. So we're going to set up an ICE table just like you see here for every one of these problems, and we're going to put all of the representative chemicals that we need to know up there across the top. This is how we're going to use this. We're going to have the initial amounts of A, B, and C, their change as they reach equilibrium, and then finally what are their concentrations at equilibrium as we go through this. So I'm going to give you two sample problems to show you how this ICE table works and how you can use it to your advantage. So in this one, the initial concentrations of A and B are 2.0 molar and 3.0 molar, respectively. The concentration of C at equilibrium was found to be 1.0 molar. We're going to use this information to calculate Keq. So let's write down what we know in the table. We know the initial concentrations of A and B are 2.0 and 3.0, and I told you that C was equal to 0 at the beginning in this simple way of going through this in Chemistry 1. We also know that C was found at equilibrium to be 1.0 molar, so we have everything we need. Now remember what I said. C is going to increase in concentration and A and B are going to decrease because we have no C, so the equation is going to move to the right. We're going to produce more products. So now that we know that, we're going to write out how much they're going to gain or lose. Notice that the amount that they gain or lose is proportional to their coefficients, their mole ratios, if you will. So A is going to lose 1x, B is going to lose 3x, and C is going to gain 2x. So it's very important that you keep in mind the coefficients when you do this kind of problem. So now let's look and see what we got for letter C here. It starts with 0 and gains 2x and has to have an equilibrium concentration of 1.0. So doesn't that mean that 2x equals 1 or x equals 0.5? So now we can replace all of those x's with 0.5. And that's what we end up getting here. So you can see in C that plus 2 times 0.5 equals plus 1.0 as the change, giving us an equilibrium of 1.0. You can also see that B is going to lose 3 times 0.x, or minus 1.5. A is going to lose 1 times x, or 1 times 0.5, giving us negative 0.5 for our change. Well, now that we know our initial amounts and the change we're going to see, we can actually figure out what our equilibrium concentrations are going to be. So 2 minus 0.5 gives us 1.5 for A. 3 minus 1.5 gives us 1.5 for B. And there's our C. So notice we have all three of our amounts at equilibrium. So now we can perform the law of mass action. And if you look here, we just put their concentrations at equilibrium in the law of mass action. There's 1.0 for C on top, raised to the power of 2, 1.5 for A, raised to the power of 1, and 1.5 for B, raised to the power of 3. And when I calculate Keq for this, I get 0.296, which shows us that reactants are favored because Keq is less than 1. A second problem we can do for calculating KEQ, or using KEQ in this case, to solve for equilibrium amounts. So essentially what this problem is going to ask us is, what are the amounts of A, B, and C if we know the equilibrium constant to be 1.5 and we're given an initial amount of each thing. So let's look. The table is going to tell us how the problem's set up. We're going to start out with an initial amount of A of 2.0 molar. B has an Na. Now, the reason why that has an Na is if you look up at the chemical equation, it's a solid. And remember, we don't put solids into the law of mass action, so we don't even care about B the whole way down. And then, as I told you before, C is going to be 0. We know the equation is going to shift to the right. We're going to actually see some products being formed. So let's look and see what the change would be. Notice that C has a coefficient of 1, so we're just going to add x to that amount. And A has a coefficient of 1, so we're just going to lose x. We don't know how much we're going to lose. We're going to figure it out using the KEQ. So if at equilibrium, what we see there is we have 2.0 minus x for A, and we have x for C. It was actually 0 plus x, but that's the same thing as x right there. So that's what we're looking at there. So let's look at our law of mass action here. 1.5 is our KEQ. I get that from up there next to the equation. And that's got to be equal to our products, which is x. And that's going to be over our reactants, which is 2 minus x. So notice everything's exactly the same. So our job here is to solve for x. So let's go ahead and start doing that. First thing I do is I want to get that 2 minus x off of that denominator, and I multiply both sides by 2 minus x. And that gives me 1.5 times the quantity 2 minus x equals x. And now we're just going to use our algebra skills, and we're going to distribute that binomial, and we're going to solve for x, which gives us 1.2. Make sure you can do that in your calculator and you understand that concept. Now that we know that x equals 1.2, we can actually find our equilibrium amounts. We know that A is equal to 2 minus x, or 2 minus 1.2, which is 0.8 molar. That's the concentration that A will be once this reaction reaches equilibrium. And for C, we know that it started at 0 and it gained x, which was 1.2, which means that C will have an equilibrium concentration of 1.2 molar. And I guarantee it, if you plug 1.2 in for C and zero 0.8 in for A, you should get 1.5 as your KEQ.